Hey Layla, you gonna behave? Hello everyone, welcome back. This week is going to be a little bit different. I did a talk on 3D printing that's about 45 minutes long, and I recorded it, and I figured I'd share it with you all. I hope that you may find it interesting, even though it's a bit different format than what I typically do for my videos. Without further ado, Layla is ready to go play, so I'm going to roll the video. Enjoy.
I actually got into 3D printing a few years ago because it sounded like a cool hobby, and I still have some experience with injection molded parts and part design and that sort of thing. So um, I ended up kind of getting sucked in and kind of trying to I guess my goal with my YouTube channel and something I like to do is to take engineering principles and step through how things work and try to explain them in a relatively easy method, so that people can kind of understand what's going on. And a lot of things, especially with like injection molding and 3D printing and a bunch of those things like that, you'll experience around you, but you never really have thought, how are those parts made? What is involved in the design, or kind of what things do you need to consider when you're designing a part that is plastic. And so today we're going to do a quick demonstration. Cross my fingers. The print is actually going to work, but I've tried to make something that will print at the same time that I am talking, so we can see kind of the finished product. But due to how some things I'm filming some things, it kind of gets a bit tricky. So the first thing we're going to start off with is really looking at if you're trying to print something like if you think about 3D printing, you might have seen it on the news or something like that. It's like, oh, you can print anything you want. Just if you break a part in your house or you want to design something amazing, you can just print anything without worrying about it. It'll just magically appear. And while that's, ideally that would be the case, that's not really the case. Someone has to design those parts, and you have to find a source for them. And so today we're really just going to look at a quick model. There's different websites like this, Thingiverse, that has different creators will have created random things, some of them useful, some of them not useful, a toothbrush holder. But what all of these have in common is really that they have something called an STL file. In this case, this model here is, someone created it and exported this STL model. And all that is, it's really just a bunch of triangles. There's not really much information stored in the file itself. If you think back maybe 20 years with video games where, we didn't have the processing power we do today, all of the characters were really blocky. That's essentially the same thing that happens with STLs. It just depends on how well they were exported, and there is no curved surface. There's just a bunch of triangles. So assuming we've downloaded a file like this STL file, then we need to process that file into a format that our 3D printer can use. So in this case, I'm using this slicer, and the word slicer is really representative of what we need to worry about, because essentially a 3D printer puts plastic down on a surface and just builds up layer by layer. So if we slice this model, what ends up happening is that you actually have a bunch of layers or slices. So each level, the 3D printer will put down plastic in a certain pattern and just keep adding layer after layer. And so in this case, there's a lot of slicing would be great if it was simple and easy, but there's actually kind of an art to it to try to get something that prints well. But in this case today, we're just going to assume that the settings here are good, and we're going to export this part, which is a G-code file, which is essentially all it's doing is saying, okay, 3D printer, I want you to go to this location in space and deposit a small amount of plastic and follow this curve. And so once it has all that information, we can jump over to, let's see here, which window do I want? The printer itself. And in this case, I have a printer that's network connected, so I can upload files right here is our astronaut G-code file that we sent over. But essentially then we can just go ahead and print the file. There's a few things though we need to worry about, and that is we need to melt the plastic somehow, and we need to deposit it on a bed or the build surface. And in this case, the extrusion temperature is around 240 degrees Celsius, which is, hot enough that it would very much burn you. So there is some concern around, like, if you have a bunch of kids running around, you don't want them, reaching into your 3D printer and grabbing the extruder. But the other thing is the build surface itself, depending on the plastic, will need to be a elevated temperature above kind of your room temperature. And in this case, it's 110 degrees Celsius, so it's fairly hot. I've stabilized this. It's been preheating for a while, so we're just going to go ahead and print this. However, before we print it, let's look. Let me switch over to the printer camera here. So here we have the printer itself. Let's make sure that you guys can see that. Yep. Okay, so the thing in the center is basically what melts the plastic. So that needs to move around in this space. We have the x-axis, kind of going back to geometry from high school. The x-axis is moving left and right, and then the y-axis we move front and back. And then in this case, the z-axis, up and down. The tool head itself doesn't actually move in that direction. The build plate itself, that orange rectangular shaped object, actually drops every time it completes one of those small layers. The build plate will keep incrementing down. But we need to know exactly where in space that tool head is. And so if you think about like a motor, like say you have your hand drill at home, that you're screwing in some screw or some object or drilling a hole. Those motors don't really have any information about how much or how fast the drill itself is rotating. If you squeeze the trigger when it's fully charged, it might be rotating at I don't know, 2,000 revolutions per minute or something like that. When the battery's dead, it's going to rotate at a slower amount until it stops. And if we did that for a 3D printer, that would be really bad, because we wouldn't know, where the part would end up. You'd essentially just have this big mass of plastic. Everything would be floating about. So in order to do that, in order to know where we are, we actually use something called a stepper motor, which actually has a positional accuracy associated with it. So if we jump back over to the this page here, this is a really good example of kind of what the stepper motor looks like inside. So you have a shaft that's attached to kind of this rotor here in the center that has some electromagnets around the outside. And if you energize those coils in a certain order, essentially that rotor in the center will rotate by a specific amount. And in general, the most typical stepper motor will have around 200 increments per rotation. So if you kept doing this order of 1, 2, 3, 4 over and over again for 200 times, you'd get a full rotation. So we can put in our software to say that, we know that, say, one rotation of this stepper motor moves the tool head by 40 millimeters or some value like that. And then we'll always know relative, to the beginning of a move to the end, exactly how far the tool head has moved. The downside, though, is that this is just a relative position. This isn't an absolute position. So we need to initially let the printer know where it is in space, and then once it knows where it's in space, it can always move to another location in that space. So what we're going to do, let me flip back over to the printer, is we're actually going to home the printer. And there's little switches on the kind of the X and Y and Z axes that the tool head will keep moving until it hits that switch, and then it'll know, okay, I'm in all the way to the right or all the way to the back of my print area. And it will keep doing that. Let me go ahead and click home. or actually this video camera is reversed right now, so it's going in a different direction. But it knows after it's going to hit this little pin right here exactly where it is in space. So theoretically, right now we could begin and print, but there's also something else about 3D printing that's important, and that is getting your first layer to actually stick to the build plate. Because if you think about those layers that we looked at the slicer earlier, each of those layers is actually really tiny. We're talking maybe 0.2 millimeters on a kind of thick layer. Sometimes you'll print all the way down to 0.1 millimeters. So it's really fine. It's a really fine line. And if this surface, this rectangular surface, is not flat, what it will end up happening is certain times the nozzle will be touching the build surface. So essentially it's the same thing as putting your finger over a garden hose. No plastic will be able to flow out of the tool head, and then nothing will print. And then in other areas, if your tool head is too far off the build plate, what ends up happening is that that plastic comes out of the nozzle and cools off before it sticks to anything. And if it does that, you end up something kind of like spaghetti. And what's really cool is actually there are people who are developing kind of an open source machine learning type code that will take a webcam image and it will detect kind of what that spaghetti or that failed print looks like, so that if you're printing along and something comes loose or something fails, it'll notify you, say via text or something like that, and you'll be able to stop the print before something gets damaged. But in this case, what we're going to do is we're actually going to use a sensor in the tool head that detects metal, and we're going to go ahead and touch that in 3 different parts of the bed. So it's detecting the actual metal of the surface, and then it can know how far away the tool head is in each of those positions. 3 points define a plane, going back to geometry again, and in this case it can actually level the bed from those 3 points. And it'll keep going around until everything is flat, because each of those screws you see that are kind of to the sides of the build plate can be independently adjusted with stepper motors, again, to adjust that plate until it's perfectly flat. The thing though with this is that in an ideal world everything would be flat, but if you're looking at the build surface, depending on how it's manufactured, there will be different kind of stresses in the part. For instance, if you think about a piece of thin metal, oftentimes it is actually made by taking a thicker sheet of metal and rolling it through 2 rollers to squeeze it down to the dimension you want. And when it does that, it actually puts kind of this stress, or the metal wants to curl up essentially. And so when you heat that, or when you cool it down, the shape of the bed may be curved, and so you actually may have like high spots or low spots. Ideally, in this case, you're actually the metal I use is called cast aluminum, which instead of rolling it to a specific thickness, it uses melted metal just into a basically a flat mold, so it doesn't have any of that stress build up into it. So hopefully it's flat, but there's always going to be some slight variation. So what we do is we do one more pass of that kind of leveling procedure by, let me pull this up here, and it probes in a variety of points across the entire build surface, and then we can create a model of what the shape of the bed is. And so then if there's a certain point where maybe the corner of the bed is a little bit further away from the nozzle, we can adjust the height of the bed as it's printing so that height is always constant. So this way we can hopefully, there's always variability in this, but hopefully we can always have a perfectly flat first layer. So it's going to continue to do this for a second. I think I have maybe a 5x5 grid here. We'll see. Yeah, that's a great question. So it's an inductive probe. So it has a specific sense distance. I think this one has, it detects when it's 8 millimeters away from the build surface. And that distance will vary depending on kind of the type of material you're using. But since this is a steel sheet, it detects it fairly well. Let me jump back over to my desktop here. And you'll see here, there's actually, this is actually kind of what it ended up creating from those 5x5 points. It creates a mesh of how high or low the build plate is. And in this case, if we scale it down, you know, it is a little over, like maybe 0.15 total, maybe 0.1 millimeters. So that's fairly flat in the grand scheme of things, but I've seen some beds that are 0.3 or 0.4 millimeters apart. And if you're trying to print a 0.2 millimeter layer height, it's a problem. So now that all that's done, we're going to go ahead and print our astronaut here. We'll jump back over to the printer here for a second. It's going to home one more time. And the cool thing about this printer is it homes off of the nozzle itself, so you always have a good kind of reference point. Right now it is printing what it's called a purge line. So since it's been sitting there preheated for 30 minutes or an hour or whatever it's been, there may be some plastic that's been melted for a long time that may be kind of like burnt essentially or charred, and we don't want that. So now it's going ahead and printing the first layer. Obviously with the tool head there, it's a little bit difficult to see exactly what's going on, but once it gets up a little bit higher, we'll be able to see better. So, okay, now that we've covered that, let me jump back to kind of some more context as far as 3D printing in general, and to do that, kind of I brought that initial question up earlier, which is, I have a 3D printer, I can print anything, anything that is plastic around me, I can recreate it in my 3D printer. And that's not actually true. So in order to understand kind of the differences between how standard plastic parts are made and 3D printed plastic parts are made, we really need to visit injection molding. And I found this cool animation here, which essentially is, this is how basically all the plastic parts around you are made, because while it costs a lot in the amount of kind of tools and parts you need, and it takes a long time to build these tools, it's really cheap because you can make a lot of parts really quickly. So pretty much everything around you is injection molded that's plastic. So what ends up happening is there's a big hopper of plastic pellets that get fed into this, let's see if there's a better, yeah, so essentially you get a bunch of plastic pellets into this screw here that compresses all of the plastic down into the end of this kind of heating area. And all the plastic that ends up in this area right here is melted. It's very well mixed. There's no more like partial pellets or anything like that. So you essentially have this shot of melted plastic that's ready to get placed into a mold. And if we jump back to the other section here, essentially what happens is that plastic gets pushed into this, which is called an injection mold. And there's generally two halves of an injection mold. There may be some more parts in more complicated kind of devices, but essentially that plastic gets shoved into this mold, the cavity between two steel large blocks. And then once that and all that plastic's been pushed in, all that plastic inside the mold gets cooled off, and then the mold opens up and the parts are pushed off of the mold. And generally for like parts that aren't super critical, they'll just get pushed off and they'll drop onto a conveyor belt or maybe a bin or something like that. For larger injection molded parts, say the front bumper of a car or something like that, there may be a robot that comes in and picks up the part and places it gently onto a conveyor. So The nice thing about injection molding is that it's fast and it's cheap. It takes a long time to set it up, but it's very cost effective. However, there's a few things you need to note about how you design a part to be injection molded, and that really is all around how the plastic flows into the mold. We want to have as even of a cross section as possible, so that like this is not a good idea to have this huge void of plastic, because as it cools down, plastic is going to contract, and when it contracts, you'll end up having a kind of like a sink where there's maybe a little divot in the outer surface of the part, and then that would be like a visual defect or something like that. The other thing is you need to make sure that the part can actually fall off the mold. So in this case, if we go over here, when the part's ejected, it needs to be able to slide off of both halves of the mold. And that's not something we really need to worry about with 3D printing, because we're just building up plastic from a surface. So let me jump over to CAD here quick. And I've just created a really basic, this is essentially a dish. And this is really easy to injection mold because, again, it's pretty much constant thickness. If we go a section view, plastic, say, could come in here and fill out this part. It'll be really easy to fall off the mold. And, we could print a lot of them. It would cool off fast. However, if we take this model, I'm going to go back over to our slicer and delete this guy. If we open up that same dish and try to 3D print it, essentially this dish represents all the things that are tricky to do with 3D printing. Because if we slice this, what we end up seeing is that with 3D printed parts, we want to have a large surface that is touching this build plate, because we need to build up off of that. If there's only a small contact area, it's more likely that the part will actually fall off or come loose during a print. So in this case, if we look at the bottom layers, there's only this very small little area here in the center touching. So this part is almost guaranteed to fail. The other thing is going to come loose from the print build plate. The other thing is that when you're building up layers after layers, you always need something else to print on top of. Because if you're printing in air, then it's just the plastic is just gonna fall to the ground instead of actually adhering to anything. So this part has a lot of what we call overhangs, which you're basically printing into mid-air. And some of that's okay. Like if we go up to the edge over here, this is actually probably close to 45 degrees, and that's fairly easy to do with a 3D printer, because each layer doesn't have a ton of unsupported area, and so the layers build up okay. But all of the surface down here, close to the base of the part, is essentially not going to work well. So there's a few ways around that, and one of which is to use supports. So if we turn on supports and slice that again, you'll see what ended up happening here is that it added a bunch of extra material around the print itself, so that each kind of area that is an overhang actually has plastic underneath it. And that's fine, that works decently well, but it takes a lot longer to print that. And even though you have all the support material underneath it, it's not a perfect support. There's still going to be little gaps where there is no plastic underneath, and it's just going to kind of look bad. As well as if you print this support material out of the same material as the part you actually want, in general it's going to adhere together, and when you remove the support, you're going to have kind of defects on the print surface. So it's going to look imperfect. It's not a part that you'd want to sell to the end user because it doesn't look good enough. that's kind of the state of where 3D printing is as a consumer. If you buy a off-the-shelf 3D printer right now, you're going to have issues like this. However, with more kind of industrial level 3D printers, they have multiple nozzles on them. So essentially what happens is the support material is made out of a different material than the bowl here essentially itself. And so what you can do with that is you can find two materials that print at similar temperatures, but they don't adhere well together, or are soluble in, say, water or some other chemical. So in this case, for instance, ABS is a really common material. It's used almost everywhere, kind of throughout your house. Car parts, etc., are made out of ABS. And then there's a material called HIPS, high impact polystyrene, that prints at a similar temperature to ABS, but again, it doesn't adhere well to it, so it can build up that support structure underneath the ABS part, but then afterwards you can either peel it off or dissolve it in limonene, which is that, if you think about like a citrus kind of smelling degreaser, limonene is the citrus smelling component of that. So you can actually just dissolve the plastic off the part and end up with the part you actually want. So that's some ways of doing it. I hope that, in the next, say, 5 years, we'll have a lot more consumer level printers that you can buy off the shelf that really do dual material prints well, but we're not at that point yet. So there's a lot of kind of fiddling with your parts to try to get them to print well. Yeah, so you could definitely print that upside down. You'd have the same issues though, where let's see if this will let me flip it. Just a second here. Yeah, so definitely, let's see here. Let it slice for a second. You'll print the outer edge better, and that'll be a lot better as far as the support on the build plate, because then you'll have a large contact area. But then essentially everything in the center, once it finishes processing here, but then everything in the center will still essentially have that same overhang issue, especially the part in the very center. So again, that's one thing. The other way is a lot of people, instead of taking a part that is designed to be injection molded and just throwing it on their printer, you design parts to be 3D printed from the first place. And that happens a lot, especially for all of the things you'll find on Thingiverse or anything like that. Parts that are designed by people who 3D print, they won't make a part that's difficult to print like this. Hopefully, at least. Some people don't really pay attention when they're designing a model in CAD, and then you'll end up with some problems. So it all depends on the level of experience the person designing the part has. Let's see here. Okay, so that's kind of the background of the tricks of 3D printing and why it's difficult. Why we're not going to, randomly be able to download the CAD of, a car and print all the parts out, because it's just not designed to do that. Next, let's take a closer look at the tool head itself, which is essentially, actually, let's jump over to the printer here for a second. Okay. It is actually printing. I had issues. Last night I printed this model a few times and had a lot of success. And then maybe an hour or two ago, I was like, let me just print it one more time, because I moved the printer around. And I realized that it was coming loose off the build plate. And that was because you'll see there's some reflections in this shot. And that's because I had to put the front cover of my printer back on, so it's an enclosed kind of volume. Essentially with ABS especially, we talked about plastic cooling down when it cools down, it contracts. And in this case, if the part contracts, it can kind of warp up off the build plate, and then if it warps enough, it'll pop loose, and then you'll have a half of an astronaut flying around your build plate, kind of hanging on for dear life, and that's never a good thing. So we don't want to replicate, what is the movie, Gravity or like The Martian or something like that. Okay, so going back to the tool head, so essentially we need to be able to extrude a very specific amount of filament, because we don't just need to get the tool head at the right position, but we need to get the correct small amount of plastic at that same location. So in this case, we're using another one of those stepper motors, so we can control exactly how much it rotates, and then based on the gears inside this component, which let me just do this quick here, not that one. Yeah, so if we go back through here, there's a series of gears attached to the stepper motor that essentially drive and grip the filament. So if we go back to the section else I had planned out here, perfect. So in this case, if we look at it from the front, there's a clear path from the very top all the way to the bottom where the filament can travel. And I realize I haven't talked about filament yet, but basically what happens in an injection mold, you take the plastic pellets, you put them in the extruder, it makes a huge amount of plastic that is melted and then shoots it into the mold. With 3D printing, we need to divide that up into essentially 2 steps. Filament manufacturer will take all those pellets and mix them into a homogeneous solid, and then extrude it into a thin string of filament that is a very controlled diameter, because we want to make sure that if we push that string of filament 5 millimeters into the tool head, that we get a very fixed volume of plastic. And in that case, the filament's coming in from the top, and then it's gripped by these gears. This doesn't quite show it exactly, but this surface has like teeth in it, essentially, to grip the gear on both, or the filament on both sides. And then that filament is pushed down into this region down here, which is typically called the hot end. And really what we're concerned about is this area down here, which has a heater block in it and a temperature sensor, and that's what the 240 degrees Celsius that we were talking about earlier is. Essentially, you want to melt the plastic at the last possible moment, because if you think about the phrase like pushing a rope, if the plastic is kind of starting to melt up in this area, then you're going to be pushing a rope of kind of flexible melted plastic all the way down into the nozzle here, where it gets extruded onto the part. And that's really difficult to control exactly how much plastic comes out of the nozzle, because it's not really stiff or strong. So we want to keep that plastic solid all the way until it gets essentially down to this area here, which is called the heat break. So everything above this point has this heatsink on it with fins. So if we jump out of the section view right now, this fan is always pushing airflow across that in order to keep that solid. And then as soon as it gets below that, it gets melted and pushed out of the nozzle. There's a few things though, again, between injection molding and 3D printing. With injection molding, they can just get a huge mass of plastic and shoot it into the mold. But with 3D printing, we need to not only extrude filament, but we also need to stop extruding filament. And to do that, there's a few ways of looking at it. The first one is to understand kind of if you're squeezing a roll of toothpaste, essentially. You have to squeeze it with a certain amount of pressure, and then the pressure pushes the viscous toothpaste through the opening. And that's very similar to how plastic is, except plastic is a little bit more viscous, maybe kind of more like honey or something like that, where it doesn't really want to go through a small opening. And so what we need to do is essentially control the pressure in this area right here of melted plastic. Because the higher the pressure, the more flow we'll get through the nozzle, and the less pressure, the less flow. So in order to do that, what we do is when we are extruding filament, we push extra filament into this area more than we actually want to extrude to build up the pressure in here so that it extrudes the correct amount. And then when we want to stop extruding filament, we actually retract filament out of this area, because if you think about if you think about the toothpaste analogy again, if you are squeezing the toothpaste but you just stop squeezing it more, the toothpaste is still going to keep oozing out of the end. What you really need to do is stop applying any pressure at all to the toothpaste, and then that plastic or the toothpaste will stop oozing. And so the combination of essentially retracting that filament and reducing the pressure in this area, combined with some predictive kind of math behind how that works, we can basically always get the correct amount of plastic out. The other thing here you'll note is these ducts. Let me get a better section view. Again, I mentioned earlier, as soon as the plastic exits the nozzle and ends up on the part, we want to make sure that that part or that plastic gets solidified in the correct shape. Because if it stays kind of in this semi-melted state for a long enough time, it might start to sag or deform, and then we won't get the shape we actually wanted. So what we have is another fan, and this fan sucks in air from the front of the tool head and pushes it down these ducts, so that you always have a stream of cool air to cool off that part that just got formed. So there's a lot into this exactly, but that is kind of the basics of it. Let's see here. I think I just heard the printer stop. And it did turn off the light. Let me just turn this back on. 1 second here. Let's see if this worked. There we go. So there, this is a 20-minute print, or I don't know how many minutes it's been, 30 minutes, is actually fairly quick in the grand scheme of things. Most of the time when you're printing something, you're going to be looking at maybe closer like hours, like 1 hour or 10 hours or something like that. But for a small thing like this, you can kind of crank it out pretty fast. You'll see here, this was printed upright, and on the back there, this plastic, let's see, the plastic is an overhang right here, and you'll see that surface quality, it's hard to see exactly on the camera. I'm trying to tilt it right. It kind of looks a little bit poor, and that's kind of why in general you need supports or to cool that plastic off as soon as it gets added to the part, so it doesn't look like that, and so it looks more like the rest of the print that is decent. So let's see, I'll leave that there. Let's see here, there's one more thing, or two more things. Let me jump back to me here. There we go. So we were talking about the pressure in the nozzle and how we can compensate for kind of the flow. And so this doesn't only come into effect when we're starting and stopping, like say if we're moving from one part of the component to another. It also affects how our corners are. And let's see if we can get this right. So essentially what's happening here is that as the printer stops and starts, as it changes direction, essentially that additional pressure that's built up in the nozzle, if it's not compensated for, essentially that extra plastic is going to end up in the corner of your part. So that's kind of what you're seeing down here at the very bottom. There's a little bit of a bulge right at the edge there. And so again, using that math of how pressure works, we can compensate for it to the point where this is about the ideal point right here, where that bulge has kind of disappeared. And then if you keep compensating too much, essentially you'll end up with not enough plastic in the corner. So with this test print, then we can kind of see, okay, I want to have the parameter at that point, and then your corners ended up getting better. The other point is with ringing. So let's see here. Go back to the printer one more time. So you'll see the brown kind of belt looking thing is around the entire printer. those are what drives the tool head into different positions. And in an ideal world, everything would be infinitely rigid. So if you had the tool head go a certain direction, it would move exactly like you commanded it to, and then it would stop exactly when you commanded it to. In reality, though, those belts are just glorified springs. And a lot of other components, even though they're, maybe much more rigid, say the aluminum extrusions or something like that, are metal, so they're stiffer. Everything is basically a spring. It just depends, how much spring and how much give it has. So when the tool head actually stops, say you're going around the edge of a cube, it doesn't actually stop. It starts vibrating. And this is kind of like, say, with noise canceling headphones. Your vibrations from the system are going to cause, let me jump back to the camera here. Your vibrations on the system are going to cause these little ripples. And as you accelerate faster and faster, those ripples are going to get more and more pronounced, to the point where, essentially the print is not good at all. However, what we can do is there's a really cool addition where essentially we calculate the frequencies that the printer is resonating at with an accelerometer, and then we can use something very much like noise canceling headphones, where you add in the opposite from the resonant frequency. So even if there's aircraft noise outside, essentially you add in a disturbance or a sound out of phase with that, and so then the vibrations cancel each other out. And that's what we can do with 3D printers, and so we can run a lot faster print times because we're not having that ringing kind of print defect. And so we've been able to increase speeds from basically twice as fast accelerations as we were able to before, and still get good surface quality without those kind of vibrations in them. So there's so many different areas like that where you can apply math or engineering or machine learning or different things like that to improve the 3D printing experience. And I really hope we'll get to a point someday where someone who doesn't know what a slicer is or doesn't know what an injection molded part is can just buy a 3D printer and press print and get a good print, with soluble supports and things like that. But we're not there yet, but definitely one day we'll be there. So that's a great question. And again, it comes down to how the plastic is or how the process is. So an injection molded part, you have a continuous a volume of plastic, so it's going to have the same properties no matter which direction you look at it. With a 3D printed part, essentially those layer lines are not homogeneous. So along the layer lines, all that plastic is all bonded together. It was all melted at the same time, but then in between the layer lines, it depends how well the next layer bonded to the previous layer. So for instance, in an ideal world, you'd actually melt the previous layer completely so that you'd have a continuous amount of ABS with no gap in between. But in reality, that doesn't happen. So you have, it's maybe 50% of the strength in the layer-to-layer adhesion versus within the layers. There's some 3D printing technologies though, what is it called? MJF, which is actually a technology HP uses that does fully melt not only the layer it's putting down, but the layer below it. So you might get up to 90% of the strength in that direction. That's actually a powder bed, and they actually print, they use their same inkjet kind of technologies to print dark material where they want the plastic to melt, and then kind of like a coolant material right next to it. And then they apply a constant kind of bar of heat that goes across the entire surface. And where there's the dark material, essentially it melts. Where there's the coolant material, that part does not melt. So, yeah, that's really a cool. That technology especially is really cool because no matter how many parts you have in the print bed, essentially the print time is the same. So you can fill it up, the volume, with as many parts as you want, and it just takes one sweep of the kind of print heads for the cooling and the marking of the filament or the plastic, and then one sweep to heat it all and melt it. So it's a really fast 3D printing technology that almost gets you to the point where you can start looking at low volume, say like thousands, not like hundreds of thousands, but like thousands to tens of thousands of small parts. But yeah, I want people to, like, 3D printing is so cool, and I think it'll open a lot of opportunities for creativity for like for instance, I'm not sure if you guys have heard of like Arduinos, like the little small electronics prototyping boards, but those didn't really come into existence, at least in my knowledge, until after I was through college. But there's so many tools now to learn and grow, not only in programming or circuit design or plastic part design, that are out there for kind of the next generation, that I'm almost jealous of all the opportunities they have. I have not done resin printing. That's something that I have considered doing. I've always been a little scared of the resin chemicals, and we have 2 cats and a dog, and I'm worried about them like somehow getting into it or something like that. But yeah, but the detail from a resin printer is just so amazing that I'll probably end up getting one time. So yeah, but also the resin printers actually, for like structural components, they're not quite as good. Certain types of plastic have something called creep, that if they're loaded under like some sort of force or load for a long period of time, essentially they'll slowly deform. They're not actually fully solid. They're kind of almost like a fluid, just on a really long time scale. And so for resin parts, a lot of the resins that are used actually have that property where it creeps. So for essentially like a structural part, like for a 3D printer, they're not the greatest, even though like you can resin print a tooth profile really well for like a belt because it has such high resolution, but eventually it'll kind of deform over time. So good question. So I've printed, so this is the printer behind me is a 10 by 10 by 10 inch build volume. I have one that I'm currently have it torn down, that's a 14 by 14 by 16 or 18 inch build volume, and I actually for a period of time I was printing something that basically filled the entire build volume. So instead of using a 0.4 millimeter nozzle that has basically the layer lines are 0.4 millimeters apart, I swapped to a larger 0.8 millimeter nozzle, and then I maxed out the flow rate of my hot end. So essentially I'd have a huge part that I needed. I work all day, figure out what I needed, and then I'd come home, press print at 5 o'clock, and go through most of a roll of filament overnight, and then when I went into work at 8 the next morning, I'd get this huge part and take it off to work and test it, and then keep on iterating. Other than probably the same YouTube videos that you've seen, that's basically the same ones I've seen, and it's really interesting. I've seen like a small kind of like car 3D printed before, but I think those are more proof of concept right now. Hopefully, that would be cool if we could just, you'd customize your home design and be able to print it, really quickly. But we'll see how the building regulations follow with that. So, but really cool opportunities there, especially when you're considering things that can't be injection molded because of the internal geometry. That's one point I didn't touch on. Essentially, 3D prints don't have to have kind of a thin continuous wall everywhere. They can have a large volume that just has infill, like small sparse lines in the middle, or you can integrate say a cooling channel inside your part that you couldn't have injection molded otherwise. So that's where they get a lot of cool advances with kind of like rocket engines and things like that, that you can just manufacture things additive, like layer by layer, that you couldn't do with any traditional kind of sense. So that's another cool thing, just printing a box that has, all the hinges and latches and features like that already implemented in the single part. Um, my coworker was talking about one. It was like a little box with a lid, and there was a gear system inside with a printed spring. So essentially, as soon as you press the latch, the box would pop open, and it was just a single part, single print with all the hinges and everything like that already assembled, which was really cool. Awesome. Well, I hope that was enjoyable and that you learned something. It was fun. Have a good one. Enjoy your weekend.